All right, friends, it's day 3 and still chugging through our look at pre-calculus mathematics on our way to calculus mathematics. Today's lesson all about one-to-one functions, why inverses matter, and the small side note, we'll give a small quiz tomorrow if you're in my class. If you're watching us on the interweb just for fun, you should also take a quiz tomorrow. So what I'd like to do is I'd like to start with a definition of what one-to-one functions are. A one-to-one function, f of x, is one-to-one. If f of a is not equal to f of b whenever a is not equal to b. Now, because this is a video, you can pause and go back and hear that again and again, but it's really not going to do a whole lot unless you fight through the notation. A function f of x is one-to-one if f of a is not equal to f of b whenever a is not equal to b. As a side note, we include here f is one-to-one if f passes what we call the horizontal line test. So you've got some function that passes the horizontal line test. Maybe it looks like that. It passes the horizontal line test. And by the horizontal line test, we mean that you can never draw a horizontal line that hits that graph more than once. So not only is that a function, it passes the vertical line test, but it's a one-to-one function, it passes the horizontal line test. And why that is significant? Well, let's pick two different values in the domain, a and b. If a and b are different, then f of a and f of b are also different. F of a is different than f of b whenever a is different than b. Now, if we move a and b, oh, that's not going to work. If we move our a and b around, you can see that no matter where a and b are, f of a and f of b will be different. But what if a function doesn't pass the horizontal line test? What if the function looks like this? This is a function, passes the vertical line test, but it doesn't pass the horizontal line test. Why does that matter? Well, because it's not one-to-one, and I can show that if I pick A out here and B out here, no big deal. But if I pick A here and B here, then f of a and f of b are the same thing. In fact, f of a and f of b give us what that horizontal line is that hits the graph more than once. So if I can draw a horizontal graph that hits the line more than hits the curve more than once, then I can find values a and b so that f of a is equal to f of b even though a is not equal to b, and so we fail the one-to-one test. Okay, so why does that matter? Well, if that's the case, if f is one-to-one, here's the big deal, then f inverse will be a function. That is the big deal. I'll even write out function. It's so important. If f is one-to-one, then f inverse is a function, and that is huge. That is huge. A quick reminder, how do you get an inverse function? F inverse is the reflection of f over the line y equals x. F inverse is the reflection of f over y equals x. So if I have some function, oh, let's see, I've got to make it one-to-one somehow. So I'll do this. That is a one-to-one function. if I draw in y equals x, then the inverse function is the reflection of that over y equals x. And you remember from your geometry that if you reflect over y equals x, xy becomes yx. So if this is the point, let's say mn, then this over here is the point nm. Algebraically speaking, to find an inverse, we switch x and y and solve for y. Algebraically, f of f inverse of x is the same as x. And f inverse of f of x is the same as x. Because if you compose a function with its inverse, because they are reflections over y equals x, you get x. So those are all equivalent statements that get made whenever you have an inverse function. A function and an inverse that is also a function. So from a practical, pragmatic standpoint, let's say I want to find f inverse of x if f of x equals x minus 2 over x plus 5, we'll just say. X minus 2 over x plus 5. So how do you do that from an algebraic standpoint? Well, I know that this is the function. This is the original function. And it is one-to-one. You can graph and find that that is a monotonic function. So no problems there. Its inverse is what happens when you switch x and y. And so if I want a nice expression for the inverse function, I have to solve for y. And that happens by cross-multiplying. And we see, wait a second, I still have two expressions with y in them. So let's kick those over to the left side, subtract y from both sides. And let's move any expression that doesn't have y to the right side. So that would be like so. And then I want to isolate y. So I want to factor out y and divide. And that means that the inverse function is negative 5x minus 2 over x minus 1. I should note, because we are reflecting over y equals x, x's become y's, y's become x's. That means that the domain of f is the same as the range of f inverse. I know that the domain of f of x, because the denominator is x plus 5, the domain of f of x is all x not equal to negative 5. So I know that the range of f inverse will be all y such that y is not equal to negative 5. I know because the domain of f inverse is x not equal to 1, then the range of the original function is y not equal to 1. I no longer have to graph and trace out to try to find a horizontal asymptote that isn't even there. I can just use properties of inverse functions to get me what I want. Okay. Hey, side note, if you're going to do this graphically, oh, not that. That. No, not that. That. Let's pretend that I'm going to use parametric functions as my graphing tool. And let's say that I wanted to graph, I don't know, maybe t cubed, where x is t and y is t cubed. And if I graph that sucker and I do it for t values from -10 to 10, I'm going to get something that looks an awful lot like the cubic function. And I'm going to get something that looks an awful lot like the cubic function because, surprise, it is the cubic function. T is x, y is t cubed, and so no surprise, that's the cubic function. If I want to graph its inverse, it's as simple as switching x and y. So how does that happen? I just put the y where the x is and the x where the y is. And if I do that, if I literally switch x and y, I get the inverse function. And it's not hard at all to throw y equals x in the middle of that picture and see, hey, I've got an inverse function. Okay, so a couple things before I'm done. There are some properties that you should know. There are some properties that you should know. First, because the exponential function and the logarithmic function, and we remember the log function, are inverses. When I compose them, I get x. Similarly, the log base a of a to the x is x. And that'll hold for a is greater than 1 and x is greater than 0. What do I mean by that? Ooh, that's not what I wanted. Here we go. Here we go. Everybody, we're gonna make it. No, not like that. Okay. So this'll really. Let's just bring up the calculator. Let's say that I wanted to graph e to the t, and then I wanted to graph its inverse like that. So the first graph is e to the x, and the second graph is the inverse of e to the x, which we all remember to be the natural log function. I should probably take a picture of that because it'll last longer. There we go. Oh, that sounded good. So we're all clear. This graph is the exponential graph. This is y equals e to the x. Its domain runs from -infinity to infinity. Its range is all positive numbers. It passes through the point 0, 1 and the point 1e. This, by contrast, is the natural log function. Its domain is the range of the exponential, so its domain is all positive numbers. Its range runs from -infinity to infinity. There is no horizontal asymptote on that blue graph. It is the slowest growing, increasing function we can think of. So it passes through 1, 0, and it passes through E1 because we just flip those x's and those y's. Man, do we remember logs? Do we? Really? Because of properties of logs, e to the ln x is x. That's a big thing to tuck away. And natural log of e to the x is x, because the exponential function and the logarithmic function are inverses one of the other. You've got to know that. You've got to know the connection between exponentials and logarithmics. You also have to know properties of logs. You've got to know properties of logs. You've got to know that if you have the log of a product, that's the same as adding the individual logs. And again, the reason why that works is because logs were created to turn multiplication problems into addition problems. There was a Scotsman, he was doing astronomy. He's saying, hey, I got to do these distances between stars. I got to square them to do these calculations. And I can't square the numbers, they're too big, so why don't we just look at their exponents on 10, that was the common logarithm at the time, why don't we look at their exponents? If we just add exponents, that's the same as multiplying the numbers. Similarly, the log of a quotient is the difference of the logs. And those statements work both ways. If you have a difference of logs, that's the same as the log of a quotient. Let's see. One more I'll need. If I'm looking to throw this thing into a calculator, if I'm looking to graph the log of x, maybe base 2. Maybe I just want the log of x base 2. The way I do that is I take the log in some base that I know about or that I can punch into my calculator. Maybe I'll pick natural log of x, and I divide it by the natural log of a. And so in so doing, I can graph any log function that I choose. Wow. Again, it's a whirlwind review of pre-calculus arithmetic. So this is stuff that should be familiar to you from your pre-calculus. I hope that this is all stuff that makes sense to you that you've seen before. All right. Very well. We'll come back together tomorrow. It'll be neat. Okay. Thanks, everybody.